Hi, friends of the sun. Welcome to our weekly reading group. And if you want to join this yourself, just hop on our Zoom and like everyone can join. All the information for that is down in the description. And today we talk with Tim about some neural network potentials, especially for solvents, and yeah, what we can do with them right now, what we can't do, the amazing generalization properties that he observed in his experiments, and yeah, how we actually can generalize to some emergent phenomena. And yeah, that's basically the coolest thing, I think. So let's go ahead and hear about that.
Great. Yeah. So thanks very much for having me. Yeah, I'm a big fan of these seminars and thanks for organizing them. I think, yeah, they're a really valuable resource. Yeah, and feel free to interrupt if you have questions or clarifications throughout the talk. I think that should be fine. It's not too long, so yeah, should have plenty of time. Yeah, so my name's Tim Duignan. I work here in Australia, in Brisbane. As I said, I was a lecturer until recently in kind of applied maths. And the thing I'm really interested in is simulating electrolyte solutions. And this is what I did my PhD in. I've been working for a long time on this problem. And I feel like just in the last year or so, we've had kind of a big, improvement in our ability to do these things. And you may have seen this kind of nice video online where we simulated this crystallization of sodium chloride, just kind of popped out of the simulation for free. We weren't even trying to do it. So this is what I'm going to talk about today, explain exactly in a bit more detail what we did here, and explain why I was so kind of surprised by it, why I think it's a significant result. So let's get started. To begin with, I think the best place to start is with kind of a little bit of history of physics. And in particular, the early part of the 20th century, you had this amazing quantum revolution, right? This new series of ideas that kind of revolutionized our understanding of nature itself, and our understanding and our ability to predict properties of nature, particularly at the atomic scale. And there's this famous quote from Paul Dirac that's very famous among physicists, where he says, "The underlying physical laws necessary for mathematical theory of a large part of physics and the whole of chemistry are thus completely known. Approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation." Okay, so this has been one of the central tasks of physics since the kind of quantum revolution around 100 years or so ago. Can you take quantum mechanics and scale it up and use it to explain the properties of larger systems, of chemistry in particular? And then, but even recently, you can even get a bit more ambitious to start to think about biology as well and other areas of science. Okay, so this is a very ambitious dream, the idea that you could use quantum mechanics to explain these high level phenomena. It's kind of, there's a whole field around this quantum chemistry, obviously focused on this kind of problem. But there's been a real central challenge in this task. And this is kind of, a lot of people will call this kind of reductionism, and they kind of may dismiss it, and they may say this is not really possible. And often what they'll do is they'll actually point to this essay by another famous physicist, Philip Anderson, written in the 1970s, called More is Different. And Anderson in this essay kind of makes the argument that when you go to larger scales, you get what are called emergent phenomena, right? Phenomena that are not observed in the properties of the smaller scale system, and that is kind of a really inherent challenge, and possibly even makes it impossible to kind of fulfill this dream that kind of Dirac has of taking quantum mechanics and scaling this up and using it to explain chemistry and biology. And there's this great quote I particularly like from this essay I just wanted to summarize, where he's talking about, the various reasons that this is really difficult. And one of these is to do with symmetries. And he says, the state of a really big system does not at all have to have the symmetry of the laws which govern it. In fact, it usually has less symmetry. The outstanding example of this is the crystal, built from a substrate of atoms and space, according to laws which express the perfect homogeneity of space. The crystal suddenly and unpredictably displays an entirely new and very beautiful symmetry. So this is a great example he's talking about of these new phenomena, the emergent phenomena that occur at the larger scale, that can have different symmetries and not be observed at all in the kind of lower scale simulations. And which means that this is really, really challenging, this idea of understanding these larger scales.
So why, like this example here of a crystal, why does it fit together with the fact that at a low scale you have more symmetry than at the emerged object?
Yeah, so the basic idea is in equivariance we impose like translational symmetry is the basic idea, right?
Yeah.
But a crystal breaks translational symmetry, so it's no longer, your simulation is no longer translationally symmetric when crystallization occurs. And so the basic idea is you can get kind of symmetry breaking. This is, physicists often condensed matter physicists often talk about this idea of symmetry breaking, which is that, you know, at these larger scale phenomena, because a key idea in kind of or kind of particle physics and so on is using symmetries in order to predict things about your systems, right? And solving differential equations using symmetries a lot. But the basic idea here is that this makes it fundamentally harder to use those ideas because symmetries are broken. So you can't, you know, you assume symmetries to solve your equations analytically often.
So Tim, if I just had my whole crystal and I were to move it, it would still be translation invariant, equivalent, whatever you do with it. But now you're saying if I have like a unit cell and translate stuff in it, it would no longer be translation equivalent. Is that what you mean?
Essentially, if you have a system that's a mixture of a liquid and a crystal,
Oh, okay.
You no longer have translational invariance, I think, right? So, you know, if you translate the whole system, it's not homogeneous, essentially. You get the sharp kind of phase transition, obviously, which means that you can't assume. So the way a lot of physicists solve problems, they assume things like, oh, this has to be homogeneous, right? Because has translational symmetry, but that's not going to work for crystals and so you actually see this. So a common way to kind of simulate liquids is using integral equation theories. But these theories are never going to capture this crystallization phenomena because they're inherently homogeneous, right?
Yeah.
So they're not going to capture. So they're just like the basic problem is if you use kind of analytical mathematical techniques, the kind of classical physical techniques to simulate liquids using kind of, you know, analytical pen and paper and so on, you'll never get crystallization out of those analytical calculations because they are essentially hard-coded translationally invariant, I guess. Does that make sense?
Okay. Yeah, sounds good.
Yeah. So this is one issue that he raises. And then the other issue he raises is that, you know, it's just, you need huge, often these things you need to simulate very, very large systems in order to see these phenomena, right? So if you just have a small number of atoms, they're never going to crystallize, right? And so this is the other problem he raises. But things have now changed, right? So he's writing this in the 1970s, and I think what he couldn't have foreseen is kind of Moore's law, right? That you get this kind of incredible expansion in our capability to simulate things. You know, we now can simulate things 1 trillion times more cheaply than when he was writing that essay. So just things have qualitatively changed when you can do that, right? And then obviously also he couldn't have foreseen all of the powerful tools coming out of the field of machine learning and AI, which give us, you know, much more powerful and useful ways to analyze large amounts of data, and particularly high dimensional data, which is exactly relevant for the kind of problems we're going to talk about. So I think we may need to revisit this idea that it's impossible to try and explain things in terms of their reduced, or predict things, new phenomena in terms of their kind of reduced or lower scale descriptions. Cool. So that's kind of the very, very high level. Now coming back to kind of what I do. So electrolyte solutions. So I did my undergraduate in New Zealand, and then I went to Australia, to Canberra, to work with a guy called Barry Ninham and a guy called Drew Parsons on modeling and simulating electrolyte solutions. And I originally wanted to work on kind of plasma physics. I thought fusion was very cool, but they kind of convinced me that actually electrolyte solutions are just as fascinating. In fact, a lot of the same physics that goes on as in plasma physics, but they're actually also incredibly important and a little bit underrated. And so you can kind of think, oh, salt and water is kind of boring and uninteresting. But I'll argue that this is one of the most interesting, but also one of the most important substances on the surface of the Earth. In fact, it's the most common substance, but it actually plays a critical role in a huge range of important phenomena. So CO2, right, is absorbed by the ocean, converted into carbonate ions. So it's an electrolyte solution, and it's playing a critical role in the balance of CO2 in our atmosphere. So if we want to understand that, we really need to understand electrolyte solutions. And then many, many more applications relevant for climate change. Aerosol formation, they're very important. All of the technologies to solve climate change, batteries, supercapacitors, minerals processing, electrolyte solutions play a critical role. But then more than that, essentially all of biology, electrolyte solutions are present, and they're not just a background medium in which proteins interact, right? They actually play an active role in a huge range of important biological phenomena. And if you want to understand all of these, you need to be able to understand and predict the properties of electrolyte solutions. So I kind of fell in love with trying to understand these solutions. And the other remarkable thing is that we really can't predict their properties at all. So we can't predict even the most basic things, like how much sodium chloride can you dissolve in water? There's no way to predict that from kind of first principles, from, you know, this kind of dream of starting from quantum mechanics. The only way, at least until now, probably, is to just simply measure how much sodium chloride you can dissolve in water. And so this is a real problem for the vast, number of applications where electrolytes are really important, because it means if you don't have good experimental data, you're essentially out of luck. So this is really why I would love to be able to predict the properties of electrolytes from first principles. So you could then kind of expand the range of which you can use these models for all these important applications.
Can you make some examples of like, so now we know how much salt can you dissolve in water of the temperature as one thing that we could want to predict. What else?
Yes.
Like when, like why, like maybe some further downstream thoughts on why it's interesting.
Yes. So a big application is minerals processing, where you dig up some rock basically, and you want to extract the valuable rock minerals from that rock and then precipitate out the ones that you want. And the way this is very often done is you dissolve it in hydrochloric acid, form like an electrolyte solution, and then add some other ions to kind of precipitate out the pure form of the mineral you want. Or you might use electrochemistry to kind of do it. And so you would really like to be able to predict, if I add this combination of ions, what solution is going to precipitate out at what concentration, is just an obvious example. And then aerosols is another one for climate change, where you want to know these, when you add sulfates to the sky, these absorb water molecules and you get little droplets of electrolytes. And you'd really like to know what is the size distribution of those droplets going to be as a function of temperature and pressure. And that's going to be determined by the free energy of those droplets, which is determined by the concentration of ions in them. Because when you put these sulfates in the atmosphere, they dissolve in water to form little droplets of hydrosulfuric acid, sorry. Does that kind of make sense? So that's one kind of key property. Just that's why you'd want to predict, these solubilities well. But then there's other things you'd want to be able to predict. Another one, a key one, is diffusivity. Is actually how quickly do these ions move through solution, and that can be very useful for all sorts of kinetic modeling of all the many processes where electrolyte solutions play a role. Does that kind of make sense?
Yeah, certainly.
Yeah. So basically, thermodynamic and kinetic properties are the things you'd like to be able to predict. Yeah, so that's kind of the dream. This field has a long history. So the classic theory of electrolyte solutions is a thing called Debye-Huckel theory. This was developed a century ago. This is kind of foundational physical chemical theory. And the basic idea is that you treat the ion-ion interactions as a dielectrically screened Coulomb interaction. So you have your system of ions, and then you have the distance between the ions, and the energy of the interaction energy. This is actually a free energy, but the energy of interaction between those two ions is given by the charges on them divided by the distance between them, plus this dielectric term, this epsilon term. And this is a very important term. This is around 80 for water. And this reduces the size of the interaction of the ions by around a factor of 80. Okay, and this is why ions can dissolve in water. They go from their crystal to kind of moving around freely in solution, because you have this large dielectric screening effect, which reduces the size of that electrostatic interaction between the ions, which would otherwise force them to kind of come together and stay in their solid phase. And so this has been the key theory. Yes, and there's all the physical chemistry textbooks. It works very well, but it only works very well at very low concentrations. So you can use this to quantitatively predict important thermodynamic properties of electrolyte solutions, in particular a thing called the activity coefficients, but only at concentrations about 10 times lower than kind of the ocean. And also a lot lower than human blood, say. So this is a real problem, because you would like to be able to predict these things at relevant concentrations up near the solubility, so you can make all these useful predictions. Okay, so this has been what I set out to do on my PhD, working with Barry and Drew, trying to extend this theory essentially to try and explain or try and get better predictions at higher concentrations, basically. And the way we did this was trying to replace this kind of Coulomb interaction, this 1 on R, which you see in the dashed line, trying to replace it with something that's more realistic. And so this white solid line is a more kind of classic example of what these interaction free energies actually look like. They have these short range oscillations as the two ions come together. And so it's actually a much more complicated interaction. And this is what we want to be able to reproduce. And as the ions come together, you can see here there's some hump here, and that's actually the energy of removing the water molecules as those two ions come into contact. And so this is the actual physical structurings, the physical size of the water molecules coming into play. But then also, to get these short-range interactions right, all of these complex quantum mechanical interactions need to be included. So you need Pauli exclusion repulsion. That's what gives you that hard wall. And then you also need, dispersion interactions, and all the quantum mechanics becomes important to explain these things, charge transfer and so on. So it's much more complex to get these short-range stuffs right. And so this is what I was doing my PhD on, trying to basically find analytical mathematical equations that could reproduce these effects, and then fitting parameters to experiment or to theory, or trying to find new ways to come up to model these complicated short range interactions. And we made some progress, but we never really, got anywhere near close to solving the problem, right? I could never quantitatively predict these kind of oscillations. And we could get some predictivity of experiment, but it was never really generalizable. It was mainly just kind of monovalent, so singly charged ions, simple ions, alkali halides and things. So really, I got a bit frustrated with this approach alone. I didn't think this was really going to crack the problem open. So then what I did was I was aware of this work from a guy called Chris Mundy and Marcel Bayer, Greg Shenter, Sean Kathman, who are at Pacific Northwest National Lab, who are doing these incredible ab initio molecular dynamics simulations, right? So these treat all of the water molecules explicitly, and they run big full quantum chemistry simulations, kind of brute forcing it. And they were doing some beautiful work on simulating electrolyte solutions, actually explaining some important scientific problems using these simulations, and doing some really nice work demonstrating that it was possible to do this. Which was very cool. And so the basic idea is that it's a molecular dynamics simulation, so it works the same way as classical molecular dynamics, which you're probably more familiar with. But you take your initial coordinates, and then rather than using a classical force field, you use quantum mechanics or density functional theory to estimate the energies and forces, right? So DFT is an approximate means of solving Schrodinger's equation, and that calculates your energies and forces. Then you use Newton's laws to update the coordinates, and then you kind of loop that procedure like a normal MD simulation to generate your trajectory, right? Just a three-dimensional movie of the positions of the atoms as a function of time. So very, very useful technique. So this is why I call this brute forcing. So you're just kind of trying to actually simulate exactly what happens as a function of time and build up a movie. And this, in the last 10 years or so, has picked up a lot, because, obviously Moore's law, bigger compute has helped a lot, but also some really nice algorithms and software, in particular a thing called CP2K, which we use, which has some nice algorithms for speeding these simulations up, such that you can start to look at kind of 100 molecules for hundreds of picoseconds, say. So that's the kind of timescales that you can look at.
When you say molecules, then you mean waters here.
Yeah, so around 100 waters, on the order of 100 waters is normally what an ab initio MD simulation you do. You wouldn't really get to 1,000 waters, I don't think. We'd be starting to really push it there.
We have like 300 atoms, and we can simulate them for a few picoseconds.
Maybe 100 picoseconds, yeah.
100 picoseconds. And how long does it take to do
that? You would need, probably weeks on a big supercomputer.
Oh, okay.
Yeah, so you're burning a lot. So that's part of the reason I went to work with these guys, because they have these big Department of Energy supercomputers, right? So you can really burn a lot of CPU hours and stuff.
And will we maybe get into that later? How much data of such simulations is there from the simulations that they run, for example?
Yes. So how much data there is at the moment?
Yeah.
Yes, we could talk about that. I'm not sure exactly how much of it's publicly available. Yeah, but that's one thing I'm talking to these guys about. They've got all these simulations they've run historically. So they probably have all this data sitting there, which I'm trying to encourage them to. Everyone who's run these ab initio simulations and is sitting on kind of old databases, I think they should try and get them out there. The problem is a lot of them didn't compute the forces, because when you're running these simulations, you'll keep track of the coordinates because that's what you're interested in, but you kind of throw the forces out because you're just doing them at every time step. So a lot of that data is gone, but I think you could still use the trajectories. So I think there's a lot of really useful data probably sitting out there on people's hard drives and things, because people have been running these for quite a few years now.
And what does this CP2K do to speed things up?
So it uses a few tricks. One is it's a hybrid method. So in DFT, you can use there's a thing called plane wave basis or Gaussian bases, the kind of two ways of treating the molecules. Plane wave, just Fourier basis. You expand the wave function in a Fourier basis, right? Or you can expand it as a sum of Gaussians. What CP2K does is use a hybrid of both of those approaches, because there's some aspects of the problem, the plane waves are better, other aspects, the Gaussians are better. So it kind of uses the best of both worlds. There's a kind of hand wavy way of explaining it. And that allows you to speed up. And then it's just written in Fortran, just, nice and fast, basically.
Okay.
But the problem is, so 100 water molecules for 100 picoseconds is nice. There's some important questions you can answer with that, but there's a lot of things that you can't look at with that. In particular, basically very little of biological relevance happens on those time scales. So a lot of interesting phenomena. Crystallization obviously doesn't happen on that time scale. So there's a lot of things you can't look at with this kind of technique directly. So you kind of want a way around it. And this is where neural network potentials come in. I'm sure a lot of you are familiar with. The basic idea is you just replace that quantum mechanical step with a neural network potential, right? Something that you've trained to reproduce this mapping between coordinates and energies and forces. And essentially you train it on the ab initio data, right? So the ab initio MD has a bunch of coordinates matched with the forces, and you're training the neural network potential to reproduce that mapping. And this has been enabled by all of the tools of modern AI. Although the idea actually goes back quite a long time to 2007 when Duignan kind of really pioneered it. Yep.
What do we lose? Like DFT is also just an approximation, right? And what does that lose us? What could we do if we did, I don't know, the ground truth, so to say, that we now can't do if we use DFT and had infinite amounts of compute?
Yeah, so you're asking about what do you lose by training on DFT?
No, like, yeah, well, that's just
as opposed to something more accurate than DFT.
Yeah.
Yeah, so DFT is an approximation and it's not perfect. I'll talk about a bit about how good it is later on. And so there's various systems where DFT will break down, basically. So systems where your electrons are highly correlated, that then gets very complicated, and often DFT won't be able to simulate those accurately. And so this is probably the kind of, superconductivity might be one example where you get complicated electronic behaviors where DFT won't be able to capture that. So DFT is an approximation, and that means that if you're training on it, there will be some cases where either it's just not accurate enough because it's using various approximations, or there's actual phenomena that it can't capture, such as interesting electronic phenomena. Yeah. Okay. That kind of makes sense. Yeah. So that is probably the biggest challenge or limitation of neural network potentials is the training data. And obviously it's only as good as your training data, and DFT is where we mostly get this training data from, although people are starting to use high-level theories in some cases. So that's kind of the biggest challenge. But the other biggest challenge, this idea has been around since the 90s actually, but Jörg Baylor and Paranello, I think, pioneered it, where they showed that you could simulate liquids with this technique in 2007, which was a kind of big breakthrough. And so this was kind of the standard neural network potentials. And so when COVID hit, I decided to really start using these things and got them working for liquid water, where they work really well. So they work well for kind of liquid water because you have a lot of training data there, right? If you simulate water, you've got hundreds of molecules, lots of forces to learn from. It really becomes a problem, though, when you try and simulate electrolyte solutions, particularly kind of low concentrations or moderate concentrations, because there your pairs of ions are much less frequent than the water molecules, right? Because there's just a lot fewer of them. So you have really limited training data on your ions. So it's actually really hard to get this technique to work. You need lots of training data in order to get it to work for electrolyte solutions, often so much training data that the approach will not really be scalable, I think, to many different electrolyte solutions. And so we needed a new tool, I think, and that tool came along in the form of equivariance, which I'm not going to explain again, but coding the symmetries into the neural network is very nice. And then this paper now, which I think it kind of was the first one to really demonstrate this really conclusively, I think, where in this footnote they pointed out they're training on 1,000 times less training data than DeepMD, which was kind of this more traditional Baylor-Paranello type approach. And so when I saw this paper, this kind of blew me away, and I thought, this is exactly what I need. So I jumped on it straight away and learned to use it and got that up and running. And I think it's borne out, at least in my work. Yes, definitely the training data requirements do seem to be much reduced, which is really nice. Okay, so there's one other piece of the puzzle I want to explain, right, which is this idea of coarse graining or continuum solvent models, which I think is very important. And so this is, you can use neural network potentials to do all atom MD, what we call it, right? So you're simulating every single atom in the system. This is a very nice approach, and people, a ton of people are now doing beautiful work with neural network potentials, many of them looking at phase transformations and all sorts of interesting work going on. So that's a really exciting field. It has an inherent limitation, though, which is you have to keep track of the position and momentum of every single atom in your system, right? And that's just inherently memory intensive. It inherently limits scaling, right? So Simon Batzner and these guys showed that you could scale these neural network potentials. I think they simulated an HIV capsid using a massive GPU cluster. So you can scale these things to huge system sizes. But, we don't have a huge GPU cluster to throw at every kind of big system we want to simulate, right? So we need to find some way of really pushing these to larger scales. And the idea is to use coarse graining here, and a particular type of coarse graining called a continuum solvent model, which I'm going to talk about. And the basic idea is this is, if you know any probability theory, this is just marginalization, right? You're just integrating out over the degrees of freedom you don't care about, right? So if you have your density as a function of the position of the ions and waters, there's your probability distribution that's given by your Boltzmann distribution. You can just integrate that over the position of all of your water molecules to get a marginalized probability distribution, which is the one that we actually really care about, right? We care about the probability of observing the ions in a given orientation, given arrangement is the thing that often that we want to calculate. And so this is, for generalizable to proteins as well, right? For a protein, often what you care about is the probability of different arrangements of the backbone of the protein. You don't really care about the probability of a water molecule, often the bulk being in some particular arrangement, right? So you want to integrate that out. So this, if you then log this marginalized probability distribution, its negative is what we call a free energy. And so this is a name that we give to this thing in statistical mechanics because it's a very useful concept in its own right. And one very useful property that this free energy has is it's also called the potential of mean force. And that's because if you take the gradient of this free energy with respect to the position of one of the ions, that's actually equal to the average force on the ion. Okay, so that's what these angled brackets here mean. That's the average, the statistical mechanical average over all of the possible water molecule orientations sampled at equilibrium. That is actually equal to the gradient of the free energy. Okay, so this is a very nice property, which means that if you want to estimate this marginalized probability distribution, what you're actually wanting to calculate is the average forces on all of your ions averaged over the orientation of the water molecules. Yeah, question?
Okay, so we have ions, we have water molecules,
Yeah.
and now we have the energies of, or the energy contributions of the waters and of our ions. And now we just look at only our ions and basically create a new function that only takes the ions as input and then gives us the energy of the of this ion configuration. But well, of course, a different water configuration could give rise to a different energy of this ion configuration. So we just average over all possible water configurations.
Exactly. That's
Like a
exactly it.
new energy function, or maybe we can call it a new potential energy function, but here you now call it a free energy because we integrated over all possible water positions.
Exactly. Yes. So it's a free energy, but it's exactly the same idea, right? It's a mapping from coordinates to energies. But now it's just the coordinates of the ions, and it's a free energy. It's a free energy because it has an entropic contribution, it's temperature dependent, and so on.
Sorry for throwing that potential word in there.
No, that's fine. That's yeah, it's the same idea. Yeah, and this is very powerful, right? So it's exactly the same thing, which means you can model it with a neural network potential, is the idea, right? So that's the basically the core idea. Because it's the same, it has the same structure as predicting potential energy. It's just you're predicting a free energy, so you can use a neural network potential to do it. And other people have done this for proteins and things. So this is not my idea. But, this is the core idea. You can use these neural network potentials to model it. Yep.
Is it correct that then your system is non-Markovian because you like,
Yes.
yeah,
Yeah. So
maybe.
the basic problem is that when you integrate out these degrees of freedom, your probabilities are correct, but it can affect the dynamics. And in fact, it will speed up the dynamics a lot. And so if you wanted to get the correct dynamics, what you have to do is add in what's called a memory dependent term to make it non-Markovian. So if you want to get the correct dynamics, you need to use a non-Markovian method of simulating it. If you just use something like Langevin dynamics, so you can take this free energy and then use Langevin dynamics to run the simulation, generate a Boltzmann distribution, that will give you the right probability distribution, but it won't give you the right dynamics. If you want to get the dynamics right, you have to use what's called a memory dependent friction term, and it's basically to account for the fact that these water molecules can do interesting different things to interfere with the dynamics. I'm not sure the best way to explain that intuitively is, but yeah. Does it kind of make sense? Cool.
Yeah.
Yeah. So yeah, and the other point is that this also benefits from equivariance. So there was a nice paper right when I was about to put this one out. Greg Voth at Chicago with Timothy Luce had a really nice paper where they showed that using they used Allegro, but they showed, you know, your training data requirements again went way down. They were training a kind of coarse-grained model representing water instead of 3 atoms, but with 1 atom. And they showed that when you used Allegro, your training data requirements were way lower than if you used kind of these older Baylor-Paranello invariant type neural network potentials. So that was a very important result as well. Okay, so just to bring it back to electrolyte solutions briefly, right? So remember these interactions I was talking about, the Debye-Huckel theory, the interaction energies we were talking about as a function of distance. Well, those actually are free energies. Those are the ion-ion interaction free energies as a function of distance with integrated out all of the solvent degrees of freedom. So this is actually what we're trying to calculate, is that free energy as these two ions come together, averaged over all of the solvent molecules. And incidentally, this is actually what you're trying to calculate. Say you're interested in ligand protein binding, right? Drug binding affinity prediction. Then this is also essentially what you want to predict. Those binding free energies, the free energies of taking your drug and sticking it to your protein. That's the quantity you're trying to interested in. You're averaging out all of the water molecule orientations. So that's more or less the same kind of problem. It's just instead of 2 ions, you now have a drug molecule and a protein. And then you also have complications with the conformational distribution of those things. But it's essentially, at its core, the same problem. So this is more general than just electrolytes. Yeah, that's my point. Okay, so now let's get into actually what we did. So the basic idea, just to recap, is you start with the Schrodinger equation, the time-independent Schrodinger equation, and we solve that using density functional theory to run ab initio molecular dynamics simulations. And so we run around 10 picoseconds or so of that, so quite a short simulation at kind of moderate concentration, 2.5 molar electrolyte solution for around, I think, 80 water molecules is what we did. Okay, and that generates our initial training data set, which we can then train and equip on to predict that coordinate to forces matching. And once you've got that, then you can run all atom neural network potential molecular dynamics with a much larger system, right? So we go to a system that's bigger, and then you can run that for much longer nanoseconds. And then I think we did one step of kind of resampling the neural network potential, recomputing the DFT forces to add to the database just to give it a bit more diversity, make it a bit more stable. And so then you can run these simulations for a very long time, which is nice. Then the next thing we do is coarse graining. So we take the neural network potential molecular dynamics simulations, we take those big simulations, and then we extract just the ion coordinates and just the forces on the ions. So we just throw away the waters and all the forces on the waters. We don't care about that. And then we train again using the QUIP, so exactly the same neural network potential. We then train it to predict the energies. So now it's a free energy of the position of the ions by getting it to reproduce the forces. Right? So we just train it to reproduce the average forces, essentially. So then it's getting that potential of mean force right, it's getting those free energies right necessarily. And then you can then take that coarse-grained, that continuum solvent neural network potential and run much, much longer neural network potential coarse-grained simulations with that. And you can look at ion pairing with those kind of things and converge these ion pairing radial distribution functions really well, and then look at activities and thermodynamic properties. And that's where we get our crystallization result, which was really nice. Okay, so and a key quantity here, which you're seeing in a minute, which I'm going to talk about a lot, is radial distribution functions, but I'll talk more about that in a second. So hopefully this makes sense as the kind of workflow. And the core idea here is that we're kind of recursively taking the output of these neural network potentials and then feeding it back into itself to generate this coarse-grained description. So it's a nice kind of recursive application of neural network potentials, which is an idea I think is really nice. Okay, so some technical information. We're using a thing called the regularized scan density functional theory approximation with a thing called density correction. We take a Hartree-Fock electron density and plug it into the R2 scan functional. I'm not going to go too much into detail about this. It gets very technical, but you can dive into this if you want. The main thing to know is that this particular level theory has been carefully benchmarked against a thing called CCSDT for water and ions. So we know it does a pretty good job for water and ions because people have looked at it for small systems where you can do really high level kind of gold standard. The CCSDT parentheses T is kind of called the gold standard quantum chemistry method. And we've really carefully benchmarked it against that, showing that it does a good job, which is quite nice. So we take around 600 frames is the total training data for the all-atom neural network potential. Again, from around 10 picoseconds of the ab initio run and an initial resampling of the neural network potential run. We've got about 80 water molecules in the initial ab initio MD. And then the neural network potential is much bigger, 500 water molecules with around 50 ions. And then we take around on the order of 10,000 frames from that neural network potential MD to train the continuum solvent model. So you need a lot more data to train the continuum solvent model because you're averaging over all the water molecules. And so you got to get that averaging right, which is why you need those longer simulations. You couldn't train the coarse-grained model straight from the ab initio MD. And then another trick that we use is we actually remember that dielectrically screened Coulomb interaction, which is, in Debye-Huckel theory, which I talked about. We actually subtract that from the training data and just train on what's left over. So it's kind of a mixed, even the all-atom one has kind of got a little bit of a mixture of a continuum model in there because we're treating the long-range electrostatics separately, calculating that analytically, because we know that does a good job, that that's the correct long-range expression. So there's a little trick there, and we find that really seems to help with the stability of the simulations. And so, yeah, the long-range electrostatics is done separate, and that's because we know these neural network potentials are only local, right? I think our cutoff is 5 to 7 angstroms, somewhere around there, and so it's not going to know about longer range stuff. And so I think you'll run into trouble if you don't have some kind of tell this information about the long-range Coulomb interaction. Okay, and then what you can do is take that simulation, extract, yep, go for it.
Maybe first, so you train on a single system.
Oh, yeah.
Right? Then you have only 600 frames of training data.
Yeah.
Okay. And then the idea is that maybe we have those 600 frames from 10 picoseconds of AI MD, and then we maybe train our neural net potential and could potentially execute this a lot faster and then simulate 1,000 picoseconds faster.
Exactly. Yeah. So you then can take, and in fact, so I think that 600 frames was actually maybe 400 from the original ab initio MD, and we actually ran just an initial neural network potential on the same size box for much longer. And then I think we took 200 frames from that and then recomputed the DFT level theory on the frames extracted from the neural network potential, and then expanded the database slightly just to give it a bit more diversity in its training data, because 10 picoseconds is really very, very short. The ion pairing is actually a lot longer timescales than that. So you barely have time for the lithium chloride ions, say, to pull apart or anything. So just to give it a bit more diversity of training data. Although it's not clear how essential that is, but we did it anyway. Does that make sense?
Yeah.
Yeah, and so the training data requirements are really amazingly low to me. I mean, and this is really NQUIP and these equivariant neural net potentials, I think, just really getting the training data down, which is remarkable to me. Yeah, and so then another thing you can do is you want to check these things, right? So you always want to check these neural network potentials. They can hallucinate. They can do unusual things. You can get weird atoms. Particularly, you'll often get like the hydrogen atom will pop off your water molecule, which is kind of physically a correct thing to do because water does self-ionize, but you don't really want it happening because it should happen at longer timescales. So these things can do weird physical things. So you always want to go back and check your forces are correct. So we then, take that final neural network potential we've trained. We've run big, long MD simulations with it, many nanoseconds, so 10 times 100 times longer than the ab initio MD, and you resample that, compute the forces with DFT again, and compare with the neural network potential predictions, and you can see you're getting almost perfect predictions from the whole trajectory. So that's very nice. These things are doing a very good job, at least predicting these structures, as long as you stay, in these kind of reasonably well sampled regions. And this is the nice thing about neural network potentials. You always have this kind of ground truth that you can go back to and compare with and just check, okay, am I doing a good job predicting the forces in this case, in this new situation, Okay, then we can look at radial distribution functions. So radial distribution functions, the way to think of them is essentially just probability distributions, right? So it's just the probability of these are the ion oxygen. So the oxygen and the water radial distribution functions. So it's just the probability of observing an oxygen at a given distance from our ion. So you can see the lithium oxygen has the smallest distance because lithium is the smallest ion, and it has this very strongly solvated water shell. That's what the sharp yellow kind of brown peak is. And so you can see we're reproducing those nicely. We train 2 separate neural networks with different seeds and then run both of them to show that they agree with each other, just to show that you're converged and that everything's working well. And you could do that for, so we've done 3 different electrolyte solutions we looked at in this paper: lithium chloride, lithium bromide, and potassium chloride. And these are the ion-oxygen radial distribution functions. And you can see we're getting those experimental peak positions really well reproduced, which is very nice. So I think now, yeah, you can predict the structure of water around an ion really accurately with this technique, which is great. The other thing which is cool is you get essentially a pure water model for free, right? So these models are trained at 2.5 molar lithium chloride. So there's around, I don't know, 20 water molecules or something per ion. So it's pretty it's kind of similar to pure water, but if you look at the radial distribution function, it actually looks quite different of those simulations. But what we can do is take the neural network potential and run a pure water simulation. And there you get this radial distribution function. So there's the oxygen-oxygen one that looks almost identical to experiment from X-ray diffraction, which is very, very nice. There's a tiny difference in the peak height, but that you can attribute actually to nuclear quantum effects, right? The fact that the hydrogen atom doesn't actually behave classically according to Newton's laws. It has some quantum indeterminacy. So that peak height position is a little bit different. But if you compare it with the thing called MD pole, you get almost perfect agreement. MD pole is a beautiful, pure water model that people made by exhaustively kind of fitting to this couple cluster, this gold standard benchmark quantum chemistry methods. So that was nice as well.
Well, this is already some kind of impressive generalization, right? We trained
Exactly.
now we have only oxygen, is that right?
So it's still water, sorry. So this is the oxygenable water.
Oh, only water, and we're looking at the oxygen radial RDFs and are getting this. Okay.
Yeah. So people have shown that you can get a nice water model with this functional out before, but I don't think people have seen this before, that you can train it at an electrolyte solution and then generalize to the pure water, which is nice. And then the other thing you see is you start kind of immediately seeing some surprising results, right? So this is the lithium radial distribution function, right? So no one has really been able to look at this before, except with classical molecular dynamics, with a classical force field. And what we see, which is new, is you see this little peak here in this kind of close range. And this is not seen in the classical force field. And these lithium ions coming really surprisingly close together, 2.68 angstroms. They're penetrating into the kind of first solvation layer. There's no water molecules in between them. I would have thought that these ions would not form the structure, just based on my intuition, based on kind of the fitting to theory, to experiment and so on. So immediately you start to see kind of surprising and interesting things, right? And this is the nature of kind of whenever you have a tool that allows you to access new scales, to look at things that haven't been seen before, nature always reveals surprising and new things. And so this is a nice kind of example with that. There's a question in the chat. Should I talk about that now? Liquid could be considered disorderly materials like amorphous materials. What is the main error of using plane wave for liquid or disordered materials? Yeah, the main error for plane waves is your cutoff. So you have to use some kind of cutoff in terms of your plane waves, in terms of how high frequency you go. And you can tune that parameter in CP2K, and we kind of can turn that parameter way up because we have we don't need much training data. So that's not really a significant source of error. So the plane waves is really fine. That's not too much of a problem. Cool. Okay, another surprising thing we saw is we can look at the chloride-chloride radial distribution function and the bromide-bromide one, right? So these are the two anions, and they actually look identical, which was also very surprising to me, right? Bromide is bigger, it should be further apart, right? And you see that in the ion-oxygen radial distribution function. You don't see it here, so that was kind of surprising to me as well. It's probably to do with the water structuring, right? It lets a hydrogen bond with both ions at once, so that's probably what's going on there, which is quite cool. The other thing we can look at is ion pairing. So you can look at, so these are the ion-ion radial distribution functions. These things are much harder to compute than the ion-oxygen ones. You need orders of magnitude more data because these are much, the pairing is much less frequent than the water molecules, at least the concentrations we're interested in. But yeah, you can compute these things with separate neural network potentials. They agree well. And the nice thing is you can then use a thing called Kirkwood-Buff theory to compute the activity coefficient derivatives. So these are a thermodynamic experimental property you can measure, basically to do with how stable the solution is. And you can see that for potassium chloride, they're a lot lower. That's because there's a more stable solution. It's more, thermodynamically favorable because the potassium chloride forms the strong contact ion pairing. You can see with a strong peak here. Whereas lithium bromide and lithium chloride do not do that really, and so they have higher experimental activity coefficient derivatives. And we can then use this theory to predict these things, and it looks like it's doing a pretty good job there, which is nice, kind of validating this. And yeah, you're getting this pairing propensity right, which is very important, right? How strongly do these ions pair with each other, which is the thing we've always wanted to be able to calculate, which is very nice. Yeah. And just another quick note is if you take the log of these radial distribution functions, you get the free energies, right? Because the log of the probabilities are the free energies. And so this is also essentially what you're doing is computing these ion-ion pairing free energies, but at high concentration. So this is a very nice result and something I've been trying to do literally for a decade. So it was incredibly satisfying to start getting these things out. Okay, now we're going to our coarse-grained model. So now we're running the coarse-grained simulations, and we can actually reproduce the radial distribution functions almost perfectly with these coarse-grained models as well, which is really nice. So these coarse-grained models are vastly cheaper, vastly more efficient. You can run them on a single CPU, converge these things in a few hours, and you can see they agree with the all-atom simulations really quantitatively, which is really nice. So that's indicating that, yes, these things are learning the correct free energy surface, and you can run simulations with them and predict these radial distribution functions, but you can converge them a lot quicker is the nice thing. So this is nice confirmation that the coarse graining is working well. And here's another thing that I was actually more excited about. So this is the free energy as a function of distance between the two ions. And so what we're doing here, so we're actually training on classical simulations here, not on the quantum mechanical simulations. So that's an important caveat. The reason we did that is we have a good ground truth for what's called the infinite dilution pairing free energy. It's called the pair potential. This is that thing that I've been talking about at the start that goes into Debye-Huckel theory. It's this free energy as a function of separation of the two ions. At infinite dilution, though, is the key thing. So it's very hard to compute that because at infinite dilution, there's only two ions. So you have to use enhanced sampling, and we use a thing called metadynamics with all atom simulations to kind of calculate the free energy as a function of distance of these two ions. Or you can just calculate the probability and then log it. Or we can calculate the average forces. There's various ways to estimate it, but it's quite expensive to estimate it because you've got to use enhanced sampling and run these simulations for a very long time. The cool thing is that you can take the coarse-grained model and you can train it on whatever concentration you like. It doesn't really matter. And then just calculate the energy as a function of distance, right? So this is a trivial calculation. You just do it, just give it the distance of two ions, calculate the energy, and that's a free energy. And you reproduce these infinite dilution pairing free energies, right? So this is the quantity that I spent my whole PhD trying to reproduce, and we're essentially just getting it for free, right? So you just train this model, train a coarse-grained model, and it gives you these ion-ion potential mean forces, which seem to be accurate compared with the all-atom simulations really accurately for free. So this was the kind of thing that I actually found this most exciting, even more exciting than the crystallization stuff, but it's a little bit less hard to convince other people they should be excited about this because it's a little bit more abstract, but I think this is just important and another example of kind of generalizability, right? So we're training at 2.5 molar, and now we're looking at the infinite dilution. So infinite dilution just means essentially two ions with nothing, with just pure water around them, right? And that's the kind of thing that you can still reproduce those properties, which is really nice. And that indicates that you could then use the model trained at a higher concentration to predict properties at very low concentration, which is very important because biology is actually very low concentration, right? I think it's 0.1 molar or something, so it's actually way lower than we use in most of these simulations. So if you want to understand biology, you're going to need a way to get at these low concentration properties without actually having to train on those low concentration simulations because it's very hard to get enough data there. And so this is indicating that this should work, which I think is important. Okay, and then the final thing that we saw, which was really nice and was actually a total surprise. So we weren't trying to look at crystallization. I didn't expect to be able to simulate crystallization with this, but Junji just came to me one day with this video and she's like, look, this is interesting. Look what's going on here. And it just blew me away, right? These things are forming a correct crystal structure of the sodium chloride ion, a salt, just by running the simulations for a very, very long time. This just kind of popped out and they just spontaneously do it, which was kind of incredibly exciting and cool to me. And this is... So the important caveat was this was trained on the classical data. So we haven't seen this trained on the quantum chemistry data yet, but I'll talk about what we have seen so far. And so this is actually crystallizing out. And so we didn't actually realize it at the time, but this is actually the physically correct behavior because the solubility of the classical model we were using is actually too low compared to experiment. It's around half molar compared to the 5 molar of the true sodium chloride. So this is an example of the classical force fields not being accurate enough. So it actually, but you never see this in the all-atom simulation, right? Because it's much too longer timescales to actually observe in the direct MD simulation. It's kind of milliseconds or longer, right? Whereas these things can only do nanoseconds or well, normally. But in some sense, this is the correct behavior, right? Because it is running above, it's called super saturated. It is running above the solubility point, so it should crystallize out. And so it's quite nice that it just spontaneously kind of sees this, right? And it's kind of impressive to me that this is stable at all. It's never seen anything like the structure. It's only seen these kind of structures that it's the beginnings, that it starts with the beginning. This is all the data it's seen, and yet somehow it can extrapolate to this very different structure and still run stably, which was kind of remarkable to me. And it's particularly remarkable because this dielectric screening, right? So here, all of these interactions, all of the Coulomb interactions are screened by the dielectric constant, right? But when you go into the crystal, there's no water molecules between them, right? So that dielectric screening goes away. So these interactions get larger by a factor of approximately 80. And yet still, it seems to be able to stably run, which is kind of remarkable. Yep. Perfect.
And like this is, or what are the properties of these? No, so first of all, right, we couldn't get this if we were to just run the DFT stuff because we need like 10 nanoseconds to observe this crystallization.
In fact, you need to run milliseconds. So no way you're ever going to do this with DFT. You can't even do it with classical MD, really, unless you have a force field that has really low solubility. So we never saw this in classical MD, even though we ran many nanoseconds. So you won't even see it in classic all-atom MD.
Okay, then why do you have this run for 10 nanoseconds points?
So this is the continuum solvent we're running it with. This is the coarse-grained model where there's no water molecules. And so what coarse graining does is it accelerates the dynamics. So we know that this is to do with that Markovian, non-Markovian property we briefly mentioned, right? Because you're not doing the proper non-Markovian thing where it has this memory-dependent friction term, you're just running, essentially a Markovian. It's not technically Markovian because you got the momentum, I guess, but it's almost Markovian. It's not technically, the dynamics are actually not correct. It's happening too fast. It should be milliseconds, but because you're not including these extra friction terms which come from integrating out the water molecules, it accelerates the dynamics. But it's actually a good thing here. And so this is the same thing people say with protein coarse graining, right? Protein, they simulate small proteins and they see them kind of fold more quickly than they should, because we know the folding process should take longer. But it's actually a good thing, right? Because you don't want to have to run your simulation for milliseconds. So if you're trying to estimate accurate dynamics, this is not going to work. But if you're trying to find the ground state, the free energy ground state, then it is useful, right? To have these accelerated dynamics. Does that kind of make sense?
Yeah. And how good are the properties of your crystal here?
Yeah, so it's the crystal structure, face center cubic. The lattice parameter is about 10% too big, but I think that may be due to the classical force field we're using.
Oh.
Okay, so yeah.
Okay.
Yeah. I haven't looked at any other properties. I imagine the other properties are not very good. I mean, if you look at phonon frequencies and things, I haven't looked at that. It's probably not great because I had no training data here, right? But you could easily fix this, right? By saying now that you know that this is the crystal structure, you could actually, I guess you'd have to add some water molecules and then get more DFT training data on kind of examples of this crystal. And then you could redo the whole thing. And people have done this. So people have done all atom MD where they add explicitly the crystal structure on the crystal, computed at DFT levels of theory, and you can simulate the crystal as well as the liquid. So in principle, you could get this right by adding explicit training data on the crystal. But you probably need to do that to get quantitative things right. That makes sense?
Then can you have a look at the comment from Juno? Oh.
What do you say? Yes, I can estimate friction, memory kernels, or position-dependent diffusivity in theory. How feasible is it in practice to reproduce nucleation dynamic kinetics from these coarse-grained simulations? Also, given that neural network potentials are known to be softened in the extrapolative regime, to what extent would this affect the thermodynamic kinetic observables for the nucleation process? Yeah, so that's a great question. So people are working on this, right? So using called, memory-dependent friction and kind of rigorously calculating these things to include into the simulation. And so in practice, I think it should be possible to explicitly include those terms to get the dynamics right. The problem is then your dynamics become so long timescales that you probably won't see it in the simulation, right? And then you have to use a thing called enhanced sampling to kind of drive it to nucleate. But once you know that this is the correct crystal structure that it wants to go to, there's different problems you might want to solve with molecular simulation. One is just knowing like what are the plausible metastable states that this could go into. And so this will be useful for that. If you want to actually directly estimate the kinetics, this is probably not the best way to go about it, right? You probably want to use just all atom MD, honestly, and use enhanced sampling to try and drive it there, and then define smart collective variables in order to try and directly estimate the kinetics. So I'm not sure this is the best way to go about computing the kinetics. it may not be useful. You may have to go to all atom MD and do enhanced sampling. I'm not sure. But honestly, kinetics is only one problem you're interested in. Very often you're interested in state of stability, thermodynamic equilibria, right? And so you're not worried about getting those kinetics right. In fact, that's probably more often what you're interested in rather than kinetics. Often these things happen so quickly that you don't really care about the kinetics that much anyway. Yeah, so the softening is a very interesting question in the extrapolative regime. That could also enhance the kinetics as well, right? So it could also be that some of this enhancement in kinetics is coming, from the softening effect, which is due to the fact that, we're training on equilibrium MD. And so that means that away from equilibrium MD, there's kind of bias to get the equilibrium right. And so, people have shown that this means away from the equilibrium, your potential energy surface is essentially a little bit soft. They're not as sharp as they should be. And that's going to accelerate kinetics as well, because it means, and so this is probably why when you run a water simulation, you sometimes see hydrogen proton hopping, you see water self-dissociation more often than you should. That's probably that softening problem. So that could also be something accelerating the dynamics. That's a relatively easy fix, though. Again, you just have to use active learning, right? So we've done no active learning here at all. But at some point, if you want to start quantitatively estimating dynamics, you're going to have to use active learning. So you're going to have to run the simulation, find your new metastable states, and then go back and do new DFT simulations to actually get data specifically on those kind of transition states, on those kind of high energy regimes, and then do an active learning loop. But that's feasible. People are doing beautiful work on this. So Paranello is doing some beautiful work looking at chemical reactions on surfaces using the active learning loops. So it's definitely a solvable problem, I think. But yeah, you're not going to get kinetics out directly from this. Almost certainly. Cool. Okay, so the other thing we did, so this was the classical force field, but then we were very interested, well, let's try with our quantum mechanical coarse-grained force fields, right? Can they get the crystals right? And so we haven't seen nucleation with these yet. But what we have seen is, and we haven't seen nucleation probably because the solubility is much higher. So the timescales are just so long that you can't even see it in the coarse-grained MD simulation. But what we can do is we can start with a crystal, so we can give it the correct experimental crystal structure and see what it does. And so this is potassium chloride with this coarse-grained model, and we're simulating it here just in an empty box. And you can see that it immediately starts disassociating and starts from the corners. And so this has actually been seen with all atom neural network potentials. You see the same phenomena. You immediately get kind of these crystals, these corners comes off first because those are the thermodynamically stable points. And then as you run it for longer, it maintains that correct crystal structure, which is very nice with the correct lattice spacing now. So you're getting that agreeing with experiment. Obviously, we had to give it to it, but it's not immediately expanding or changing the crystal shape, which is nice. And then as you run it, you get this gradual dissolution. And the nice thing is around now, you should see it rapidly dissolving. Yeah, so see how it kind of it slowly shrinks and it rapidly dissolves. That's a thing called the critical nuclei size. Below that size, it's no longer thermodynamically stable and it kind of rapidly dissolves and disintegrates. So, it seems to be following the correct physical pathway as well, even though it's never seen a crystal. It's only seen this kind of disordered solution phase training data, which is very exciting too. Great. Okay, and then just wanted to finish up on this is a little bit controversial idea, maybe a little bit grand scheme of things. But what I'm wondering is this a more general tool for this problem of connecting scales? And this is something, Greg Shenter and Chris Mundy and everyone at PNL always talked about because they're doing these ab initio simulations, but they were always really interested in these macroscopic phenomena. And they'd always talk about this problem of connecting scales. It's also called multi-scale simulation, right? How do you take quantum mechanical information and use it to inform molecular scale simulations rather than just trying to build a simulation at each time, trying to hand build a kind of model for each scale you're interested in simulating? Is there some way where you can connect these scales? You can take information from the lower scale and feed it up to the higher scale, and then do that potentially in reverse as well with perhaps active learning or something. And so this is kind of, this more general kind of argument that I want to put forward is a little bit more controversial. Maybe these equivariant neural network potentials are kind of a general tool for doing this, for taking this quantum chemistry data and connecting us to the larger scales, which is quite an exciting idea because this has been kind of a central problem in physics for, literally since quantum mechanics, really. And there are some other interesting implications of this. So this is more general than just electrolyte solutions, right? So people are using this technique, at least this coarse graining neural network potential idea, to simulate proteins now. And there's some really exciting work on that. You can also start to think about something like AlphaFold 3, right? So AlphaFold 3 is a diffusion model now, right? So they've moved, towards, so it's kind of coming back to this molecular simulation regime because a diffusion model runs Langevin dynamics, which is a molecular simulation algorithm So you're doing on a free energy surface essentially, because you got the score, which is essentially a vector field acting on your coordinates, and you're updating your positions. So you're actually running essentially molecular simulation. And there's this beautiful paper from Marlowe's Arts and Rian Vandenberg at Microsoft showing that if you train a diffusion model on MD simulation, your score is actually equal to the PMF. So this coarse-grained models is actually rapidly improving. So this is just another kind of point. These are more general. And so there's a question of, is this, are we replacing MD, or are we just moving back towards molecular dynamic simulation, but continuum solvent molecular dynamic simulation now, which is a very interesting question. And so the conclusions are, I think this approach is ready to scale. I think we need to start applying this to many electrolyte solutions, different concentrations, temperatures, building up a database of properties, right? I think that's one important thing to do. And this will be really important for many applications, particularly climate change and biology. I think the DFT is accurate enough as long as you carefully benchmark it and make sure your quantum chemistry, against high-level quantum chemistry methods like CCSDT, and show it's doing a good job. Equivariant neural network potentials are potentially, a powerful general tool for connecting scales and physical simulations, which is what I'm even more excited about more generally. And these things are surprisingly capable of predicting, well outside where you would think they would be able to based on where the training data is. So thanks very much.
Okay, thank you. What do you think will be the most production-ready deployment of something similar to what we talked about today? Like what application that has some real world use right now?
Yeah, great question. I mean, this is what I'm trying to work out now. So there are a ton of things you could look at. One is, so there are a lot of minerals processing processes, basically, as I was talking about before, where you're taking minerals, trying to dissolve them in electrolyte solution, and then precipitate them out. So the way they model those at the moment is they use kind of this, basically something like this Debye-Huckel theory we talked about, but they add some extra terms to the equations with fitted parameters that they fit to experiment. Okay, and so we only have good models in cases we have good experimental data. And that is actually quite limited. So as soon as you have an unusual temperature or a pressure or an unusual ion, you're immediately out of luck. And so that's one direction you could go, right? It's just saying, well, let's basically simulate things at temperatures and pressures and get high quality data that you could then use to model these important minerals processing steps. I think that's one important thing that could be done. And particularly in many cases, higher temperature is often very hard and expensive to get the experimental data, right? Because if you're 100 degrees or something, a lot of your experimental equipment's not going to withstand that. You have all sorts of problems. It's very expensive, So if you could just simulate, in fact, things converge quicker with high temperature. So that's one potential thing you can do. Another thing is just actually just getting molecular scale information. So a lot of these cases, people don't even know, so you might have a battery application, for example, and you don't know, what are the actual, as a function of pH, temperature, and pressure, what are the structures, what are the molecular cell structures that are forming around these ions? So that's something I'm looking at now, is simulating more complex battery electrolytes to actually give physical insight, molecular scale insight into what's actually going on as a function of pH and temperature and pressure in terms of the molecular scale details. So you can then use that to inform, your design of the battery, potentially. So yeah, there's a few different directions you could go to, but there's kind of two main buckets I think of it. One is estimating, is replacing experimental data, right? So at the moment you need experiment to model everything. You need experiment to get the parameters for your model to model these things. Could you just replace that? And then the other thing is just actually getting insight, molecular scale insight that we haven't been able to get previously because we don't have a microscope with picosecond angstrom scale resolution, right? There's no way to see these kind of things with a microscope. So, just a computational microscope is the basic idea, right? Can you just use these simulations to just look and see what's happening at the scale? So those are the two kind of buckets of applications. And it's an interesting idea. I think, yeah, there's so many places electrolytes are important that it's hard to narrow one down. But another really important one I want to do is just aerosol modeling, right? So I want to model the free energy of these little droplets that form in the atmosphere of electrolyte solution as a function of temperature and pressure, because that's one of the biggest sources of errors in climate change models currently is we don't know and this is really important, we saw this massive spike in temperatures in the North Atlantic when they pulled all these sulfate emissions out. We don't know how to model, as far as I understand it. The climate models have no way of accounting for or predicting, given this level of emissions, given we put this amount of sulfate in the atmosphere, what is the size distribution of droplets going to be? Because then you could predict the reflectivity of it. So, and this is going to be an incredibly important problem as climate change gets worse, which I think it's going to do. Someone may just, Bangladesh or someone may get sick of, sea level rise and just start putting these sulfates up there. So we really need to know what happens. If you deliberately put sulfates in the sky, we need to have really precise simulations of exactly what it's going to do. And I don't think we are there yet. So that's another thing I think that could be quite important. I think this could be useful for that, kind of building these models. You could then take that data and plug that into a climate model to more accurately model what happens when you put sulfates in the atmosphere.
Okay, then let's maybe say the more academic part of the more researchy part of the conversation is more or less finished, and I want to thank you, Tim, for presenting here. And like if you have further questions, then I would say from now on, let's maybe put them to email or so. I'm sure Tim is happy to answer via email. And if you have any last words, Tim, then go ahead and say them. But otherwise, I would have some other questions that are maybe less research related.
Cool. No, yeah, thanks everyone for coming along. Thanks for the great questions. Yeah, and feel free to email me. Yeah, always interested in chatting more.
Yeah, then how do you come up with these applications? Like, how did you hear about this? Calculating the size of droplets in air or aerosol droplets in the air.
That's a good question. How did I come across that? I mean, it is very hard, eh? Yeah. So, it's very hard to know, yeah, what's important and where the problems are, basically. Like, what are the challenges? What are the actual challenges? So this is something I'm struggling with at the moment, like trying to talk to people in the mining industry, like what are the actual problems that they're facing that need to be solved, right? So one thing is one really nice idea, which I like, is just talking to people and asking them what their problems are. So talking to people in an industry or wherever and just finding out like what are the actual problems you struggle with, and then thinking about, are there any ways, the techniques I could work on could solve this? Because there's a lot of people kind of working on, things that are well-established problems, but there's so many problems out there that people aren't working on, right? So yeah, it's a really huge, I guess, alpha you call it or whatever. If you can find, problems that people don't know about or people don't think are particularly important or aren't solvable, yeah. So it's a really important problem. I'm not sure that I have good advice on it other than to talk to a lot of people, just read a lot. Yeah, it's a good question. How do I work out, what are just a lot of Googling, basically. Just Wikipedia, okay. Wikipedia rabbit holes, just looking for, I mean, the climate thing is interesting, because it just popped up, because aerosols, have been in the news basically. So I was just like, well, why can't we predict what these aerosols are going to do? And then you just dig into it and see like, oh, here's the problem. It's because they're forming these little droplets. Yeah, it's a good question. Okay. I don't know. Yeah. I don't think I have a good answer, sorry.
Yeah, I'm just wondering now, like what other applications might be out there. Maybe there's some battery people that care a lot about some equilibrium stuff as well, and are stuck because they can't predict those properties, and then whatever you would produce would be super helpful or something like that.
Yeah, I mean, one thing to do, so the activity coefficients one is interesting. So that's like you basically just pick up a physical chemistry textbook, right? And you start reading, and you'll get to Debye-Hückel theory, and they'll explain that, and then they'll say, and at high concentrations, this doesn't work, right? And then so that's the way you find that problem, right? I mean, you just pick up a textbook and read it and just see like what is the state of the art and where does it break, and that's how you find your problems, right? So that one's not actually too hard to find. That's been a problem of physical chemistry for a century, right? So you just pick up a textbook in any discipline, start reading it, and see what the state of the art is, see like what can be modeled and what can't be modeled, basically.
Then, because you mentioned Debye-Hückel now again, I'm not sure how to pronounce it, but my teachers always pronounce it Debye-Hückel.
Oh, what is it, sorry?
Debye.
I have no idea. Yeah. Interesting. Yeah, I have no idea. That's probably totally wrong. No, I am almost there. I only read it, so I'm not even sure. But so I'm saying Hückel, right? But it's Debye that's wrong, is it? That's interesting. Yeah, that's probably right. It's probably American.
Then I guess if you don't mind, let's maybe go for, okay, Karim unrests their hand. Then,
No, I didn't. Sorry, I was auto.
go ahead.
Yeah, so I maybe have one idea for, or I would like to ask if it's a possible application. So I've been working on a project where it was mostly experimental, so we used Bayesian optimization because we couldn't simulate, or at least from my skill set, couldn't simulate it, um, to have morphology-specific crystal growth. So for example, synthesizing nanorods of some certain type of crystals. Could you, and then it was all mixed with a complex hydrodynamics and flow profile. How far away would you say are we from mixing that with essentially like, yeah, fluid mixing with mixing conditions to say, okay, if I run these conditions, then my crystals will be 90% of this specific morphology?
Yeah, that's a great question. And that's the dream, right? That would be amazing if you could do that. Before we saw this crystallization, I would have said that's a long way off. But now that we saw that spontaneous crystallization, I think maybe not so far off. So yeah, so what are the challenges? I mean, so the dynamic, the fact that it gets the dynamics wrong is probably, it may still be an issue, right? Because there are certain cases where there'll be one thermodynamically stable state, but it's actually the dynamics that determine what state you're going to get. So it may be a problem if it gets the relative dynamics wrong. That could be an issue. But other than that, I think it's it could be feasible. I mean, I hesitate to say it would work. I mean, I'm sure there would be problems that would crop up when you tried to go at it. It depends on what kind of species you're looking at. If you're looking at crystallization of salts, I mean, I think it may be feasible, but I imagine you're looking at something more complicated,
Yeah.
like carbon
No,
nanotubes or
actually
something.
not. In our case, it was zinc oxide nanoparticles. So
Zinc oxide
just
nanoparticles, yeah.
hydroxide solution mixed with zinc precursor, and then they precipitate out.
Maybe. I would love to do that, yeah. I don't think there's anything fundamental stopping that. If you have actual chemical reactions, it's going to get more complicated, right? Because here you just kind of have these ions coming together. If you have
Mhm.
chemistry going
True.
on, electron transfer essentially, it's probably going to get redox reactions. It's going to get harder. So I wouldn't tackle something that has kind of redox, chemistry going on at first. But definitely, I think this is where I would love to take it in this direction, basically, yeah. Yes. So yeah, whether you would use the continuum solvent approximation, I think you'd probably need to look at the timescales where the stuff happens at, and whether that. But I think it should be doable. I mean, I think it should be possible. It's definitely possible.